My name is James Edward Camus. I'm a retired professional geologist with 40 years experience. I'm here to present to you the Plate Climatology Theory, how geological forces influence, alter, or control Earth's climate and climate-related events. Now, I'm not here today to prove that this theory is correct, nor am I here today to prove that the global warming climate change theory is incorrect. Rather, today's presentation is a geologist's perspective of the power and climate influence of geological forces. The idea about this theory came to me in 1977 when, as a young graduate student, I saw something amazing happen. The 1977 dive of the Alvin submarine along the Galapagos Islands, which are volcanically active deep ocean fault area. What they found on this research dive really changed my life. They found a whole new system of life on Earth that no one knew of. They termed it chemosynthetic life. It was life that was supported without light, like photosynthesis, but life that was supported by hot fluids emitting from ocean floor volcanoes and vents. The fluid was chemically charged. All of these animals lived off this hot fluid. It just amazed me. As a geologist who had been studying continental drift, or plate tectonics, where continents move and break, especially they break along the ocean floor, I put two and two together and I said, hey, there's a lot going on in the ocean that we don't know about. This heat that's coming out of these plate boundaries really must have a big influence. So for many years after that, I continued to think about this idea and develop it. So eventually, I found out that there was more to the story, that the oceans were actually influencing the atmosphere and the climate. The idea of the plate climatology theory was introduced in October 7th of 2014. You can refer to my plate climatology website for details of what I'm going to present today. There's over 80 articles. The references for all the articles and for the presentation today are located on this website. The powerful and significant climate effect of geological forces has been greatly underestimated and underappreciated and has remained hidden for several reasons. First, remoteness. 71% of Earth is covered by oceans, with an average depth of 14,000 feet. These regions also are home to most of the big fault boundaries that border continents and ocean segments. They're known as plate boundaries. Another 11% of Earth is covered by polar ice caps. Some of it is 5,000 feet of glacial ice. In other areas, it's very thick sea ice. These areas are very remote. They also contain some very large fault systems beneath them. So in total, 71, 11, approximately 82% of Earth is remote. The second reason that geological features haven't been appreciated is lack of monitoring. These remote areas do not have systems that record on a regular basis heat, CO2, methane, iron, mercury, on emissions from these geological features. As a result, there's very little known about them. The last reason is what I'll term atmospheric bias. Now, I want to make sure that I insert here that this is not intended to be some kind of political statement, nor am I trying to demean very hardworking, intelligent scientists or universities. So atmospheric bias is this. Looking at this atmospheric data set, which they had available to them, they did in fact find correlations between atmospheric parameters and climate patterns and climate events. I believe that many of these correlations are actually side effects of the driving force, the root cause of these things, the ocean and ocean heat flow, and in some cases, land volcanoes and land fault systems. So atmospheric bias has acted to hide the important influence of geological features. So that we're all on the same page about the premise of the theory, I'm going to read to you this statement. Increased tectonic activity, either locally or globally, equates to more heat and chemically charged heated fluid release from active geological features into oceans, subglacial polar areas, and atmosphere. This altered heat and fluid input has in past, and still to this day, acts to affect Earth's climate and climate-related events. As you see here on the slide, the many connections between geology and climate are as follows. Melt the base of polar ice caps, generate all El Nino-La Nina events, alter ocean currents and chemistry, and I'll let you read the rest of those below there. The top three we're going to discuss in a little more detail. Today's presentation of evidence supporting the plate climatology theory will be broken into 5 segments: Antarctica, the Arctic Ocean region, and the Western Pacific Ocean, specifically the El Nino-La Nina event. Ice ages and continental volcanic emissions. So let's go on to Antarctica. I want to make sure that you understand up front that Antarctica is still under intense evaluation and research. So what I'm presenting today is not absolutes, rather it's reflection of the best knowledge present to me at this time. I think it's pretty convincing, but just want to make sure you know that there's still things to be discovered about the geology and Antarctica in general. The left image places Antarctic continent in perspective with the USA. You can see that it's much larger. It also shows that Antarctica is broken into 2 pieces. On the west is West Antarctica. You note that the upper portion of West Antarctica kind of forms a thumb that's called the Antarctic Peninsula. The remaining 80% of Antarctica is termed East Antarctica. The right image shows a NASA graph that reflects ice melting on the entire continent from 1995 to 2015. It's here shown as a proxy for ice melting, reflected as millimeter sea rise from the ice melting in Antarctica. You'll note that West Antarctica, the smaller 20% segment, accounts for 100% of the continent's ice loss. Make sure you note that West Antarctic Peninsula is included in the 100%. Also, you'll see that East Antarctica, the much larger 80% segment, is actually gaining ice. This graph is substantiated by a 2015 NASA research study by their senior glaciologist, Jay Zwilly. So exactly why is 100% of the melting in the Antarctic continent contributed to the smaller 20% area? This map is the answer. It is the University of Washington's Antarctic 50-year average surface temperature map. It was generated in 2009 by Dr. Eric Stieg, and its validity was hotly debated for many years. However, since that time, it has been proven correct by 2 more modern research studies, NASA's Skin Temperature Map and British Antarctic Survey's Temperature Map. Now, a surface temperature map that Dr. Stieg made represents the upper few meters of temperature of the sediments and the ice. It does not include atmospheric readings. So in that sense, it's a good measure of the heat being emitted from the Antarctic continent. The map was very controversial for several reasons. First of all, it didn't show the expected uniform heat flow across the entire continent. Instead, it showed a very sharply defined, in red, hot area. You can see on the left or west and the right or east, it's a very sharp transition to the moderately warming or non-warming East Antarctica. So why is there a sharply defined warming area in Antarctica? This is the answer. This map shows in black hatched line the largest geological feature on Antarctica. It is the 4,000-mile long and 700-mile wide geological feature called the West Antarctic Rift. Now, this feature is actually ripping the entire Antarctic continent apart. It's home to 149 land volcanoes at latest count, some subsea volcanoes, and a 620,000 square mile hotspot. So what we're going to do today is we're going to take a look at 4 areas along this giant rift. we're not going to try and talk about the complex geological history of these spots. Rather, we're going to talk about the heat flow from these spots and how it reflects on the overall heat flow of the Antarctic Rift. The left image shows the northwest extension of the Western Antarctic Rift and its major fault traces, red, as the fault traces continue into the ocean. Also on here are some yellow circles. Those are active volcanoes, some of them recently erupting. The larger the circle, the more active the volcano. So first we'll talk about the South Georgia Islands. That is imaged on the upper right slide, where you can see that in September of 29th of 2016, 3 volcanoes erupted simultaneously, indicating that this is a very active portion of the rift. On the lower right is the May 1st, 2016 eruption of Mount Currie, which is located in the South Sandwich Islands. This eruption emitted tremendous amounts of volcanic ash onto the surrounding glacial areas of ice. It disrupted penguin migrations, but they adapted. They didn't die. And I think this is kind of an interesting aspect of this eruption. As you may know, the Galapagos Islands are volcanic, and Charles Darwin did his research there. He discovered that the geological eruptions and changes on these islands had a strong influence on the extinction or the preservation of specific species there. Based on this, he developed his theory of natural selection. So that's kind of what's happening in this segment of the Antarctic Rift. Now we're going to switch to another area along the rift. This is the South Shetland Islands portion of the rift. Again, you can see the strings of volcanoes, the long linear string of volcanoes, where there's 6 of them, one very large, is called the South Shetland Islands specifically. This is an area that contains one of the most active volcanoes in all of Antarctica. It's called the Deception Island Collapse Caldera. Now, for those of you that don't know what a collapse caldera is, it's a huge volcano that erupts so violently that the center of it collapses. It's often filled with fresh water, or in this case, because it's close to the ocean, this huge hole is filled with seawater. In fact, there's a little opening in this large caldera so that ecotourists can come and visit it. On the right slide is the interior of the collapsed caldera. You can see the tourists soaking there in steaming hot water on black volcanic sand. The reason is that this caldera is still active. It's one of the first stops on visits to Antarctica. Now, for myself, as a geologist, I'd be very skeptical about soaking in water in the center of an active collapse caldera, especially since this specific volcano has erupted on 10 times since 1827. Last eruption was 1995. The other thing I'd be a little worried about is being ferried back and forth from the mothership, and what you can see on the right slide is a rubber raft. Just a little bit of humor in there. But this is definitely a very active feature in West Antarctica. Next, we're going to shift down to the Byrd area, which is the central and main portion of the West Antarctic Rift. On the left is this area. We're going to talk about 3 things: the Hudson Mountain Volcanic Area, the Mount Takahe Volcanic Complex, and lastly, the Pine Island Glacier. Concerning the Hudson Mountain Volcanic Area, in 2008, research by the British Antarctic Survey proved that 2,200 years ago, a massive subglacial volcanic eruption punched through the overlying ice and covered this ancient glacial area in a thick layer of volcanic ash. Post-eruption glacial ice accumulations then buried the ash layer. Based on ice cores taken by the British Arctic Survey, they were able to map the extent and the thickness of this interglacial ash layer. They therefore realized that this was one of the largest eruptions in the Antarctic region in the last 10,000 years. Now shifting to the Mount Takahe volcanic region, again shown on the left slide, outlined in red. You'll see 2 red circles. These are huge volcanoes that punch up into the glacial ice. They don't make it through it. The one in the far lower corner is Mount Takahe. Research released on September 2013 by the Nevada DR Institute showed that 17,700 years ago, Mount Takahe erupted on multiple occasions during a 192-year span. This world-class eruption, according to their research, acted to alter ocean currents and climate of the entire southern hemisphere, extending from therefore the South Pole to the tropics. Lastly, we're going to discuss the Pine Island Glacier. On the left slide, you can see that it's a long linear glacier. It's actually there because of faults. On the far left of this image, not shown, is the west-bounding main fault of the West Antarctic Rift. You can see that these other valleys in here, north-south valleys, are very linear, including the Pine Island Glacier. They're a reflection of secondary faults associated with the main rift. The Pine Island Glacier was for many years considered to be the worldwide poster child of how global warming is melting glaciers. Hundreds of media and scientific articles claimed with certainty, in fact 100% certainty, that this was proof that anthropogenic warming of our planet was active right here in Antarctica. So again, let me stop here and emphasize, I'm not trying to discredit the hard work of these scientists or the media. Rather, I'm just trying to demonstrate that in science, some things are not what they seem to be. So now back to the Pine Island Glacier. In 2018, researchers from the National Science Foundation made a stunning discovery. They confirmed the presence of a currently erupting volcano beneath the Pine Island Glacier. So science was turned on its head. The melting of the Pine Island Glacier is actually the result of an active subglacial volcano. On the left image is the Pine Island Glacier, its catchment basin, outlined in blue hatched, and the volcanoes which have been mapped under the Pine Island Glacier. Of interest is also the adjacent Thwartes Glacier, its catchment basin again outlined in blue, and the active volcanoes under it. You may have seen in the media over the last couple of months scientific articles saying that they discovered a huge air cavity beneath the ice and above the bedrock surface in the Thwartes Glacier. Again, these reports contended that it was the result of human atmospheric warming. I would contend here that since we already know there's an erupting volcano beneath Pine Island, it's logical to presume that the cavity in the Thwartes Glacier is the result of a volcanic eruption of one of the 40 volcanoes under it. Now we kind of stay in the same general area of West Antarctica, but we expand out a bit and look at the largest geological feature along the rift. It's the 620,000 square mile Sub-Glacial Byrd Mantle Plume Hotspot. So it's outlined again in red there on this image. For those of you that don't know what a mantle plume hotspot is, it's a huge area of magma that comes up from the mantle, inner earth reaches, goes up to the layers, rock layers of the outer crust of the earth. Here it kind of hits them and spreads out in a mushroom shape. So this is a big, huge, widespread area of magma. In many cases, this magma puts extensive pressure on the surface layers of the rock. They fail, and volcanoes pop through the layers of the rock. That's what's happening in the Pine Island and Thwartes Glacier area that we previously talked about. Also on the map above are shaded red areas. This is NASA's melting report of ice. It represents melting from 1992 to present. So red shaded areas indicate intense melting. You'll notice the very close correlation of red areas to the outline of the Byrd mantle plume. To me, this is strong evidence that there is a cause and effect relationship. One other interesting thing about the Byrd mantle plume area is that other research has shown that during the last few decades, this area has been rapidly rising. The bedrock is pushing up and it's uplifting the entire glacial area. This is very, very typical evidence of what mantle plumes do, especially when they're active. The magma pushes up the rock. Researchers have claimed that this is not mantle plume origin, but rather glacial rebound. In other words, when you melt the glaciers, you release pressure and the bedrock beneath it rebounds and goes up. Other research has shown that this is not correct. The rate of uplift of this area is way too great to be explained by glacial rebound. So clearly, the ice sheet melting and the uplift in this area is related to the mantle plume. Now we're going to move farther south. Still on this image, you see the area that's marked the Mount Erebus volcanic complex. We're going to skip over to that. This is Mount Erebus on the left side. Not an image that you would normally associate with Antarctica. Mount Erebus and the volcanic complex which it's involved in, which is 275 miles long and 150 miles wide, is a very active volcanic platform. Mount Erebus, a 12,433-foot high stratovolcano, has been mildly erupting for many times. What you see here is one of the pulses of the greater eruption of this volcano. Research by an Indiana university, they shot seismic over this, and they were able to determine that the magma chamber that is fueling the Mount Erebus eruptions has recently moved from deep down to within 4,000 feet of the summit, kind of adding to the idea that this volcanic plateau area is very active. The right image places the Mount Erebus, marked there, and two other volcanoes in this area in perspective. Of note, on the right is a black hatched line. This line represents the easternmost major bounding fault of the Antarctic rift. So you can see also on this image break up ice, large chunks of ice in the bay water that are breaking up. You can also see something marked down to the south there called the Nansen Glacier. The Nansen Glacier has also been in the media reports and scientific reports as a clear indication that atmospheric warming is working on the Nansen Glacier and making it rapidly retreat. I would contend this is not correct. I would contend, since you have an erupting volcano in the same bay and you have an active fault that cuts through the Nansen Glacier, that geological heat flow is the more logical reason for retreat of the Nansen Glacier. Now we're going to switch to an offshore volcanic platform in East Antarctica. It's called the Kerguelen Plateau. It is one of the largest igneous provinces in the world. This ocean floor plateau and a few islands cover 480,000 square miles. They rise 6,600 feet above the surrounding ocean basin. The plateau is also home to numerous volcanic islands, ocean floor volcanoes, and hundreds of active ocean floor thermal vents. In 2016, a study by the Kerguelen Plateau by the Australian Antarctic Research Institute concluded the following. This area's extensive recurring plankton blooms are strongly aided by iron enrichment of seawater emitted from thousands of hydrothermal vents. Secondly, the sudden alteration of marine animal migration patterns, specifically walruses, sea lions, and actually fishing patterns, are related to volcanic activity, not atmospheric warming. Therefore, they concluded that this area is very geologically active. There's another aspect to this research. The original mission of the British Antarctic Survey research was kicked off by reports from fishermen that marine animal migration patterns had dramatically changed. It affected their fishing. They noticed that the sea lions and other animals were moving to spots they never had before. They felt that this indicated that there was an ecological disaster going on in this area. They put together money, took off on a research study. When their vessel got to the Kerguelen Plateau, they witnessed something amazing. One of the islands, the Herd Island, its volcano, Big Ben, was actively erupting. This is a 9,600-foot volcano. So they anchored up their vessel and they launched their self-guided mini-subs to discover what was going on in and around this volcano. What they found were, on the first week, hundreds of active hydrothermal vents emitting massive amounts of iron-rich fluid into the Kerguelen Plateau. So that is how they had to change their original hypothesis from a man-made ecological disaster to something that was controlled by heat flow from active terrestrial volcanoes and ocean floor volcanoes. The story really has other implications to it too, because again, it's an indication how science isn't always what it appears. So we need to be a little careful about presuming one thing without researching everything. To me, of course, the geology. Now we move to an offshore area on the north side of East Antarctica to investigate a melt hole that appeared very suddenly in the year 2017. On the left slide, that melt hole is shown as a blue spot. On the right is an image that kind of zooms in on that area. The sea ice is noted in white hatched. The outline of the melt hole, kind of on the right side of this image, is a white circular area. At the time this melt hole was discovered, scientists decided that it was probably the result of deep ocean currents making their way laterally to this area of the melt hole. This area of the melt hole is a high, it's called a rise, a seafloor rise, specifically the Maud Rise. They felt that these ocean currents hit this rise, went upward, and these warm ocean currents melted the hole. There's a problem with that hypothesis. First of all, there are other high areas in this region. None of them have shown any melting. Secondly, this melt hole also appeared previously in the year 1976, and it had occurred at the exact same position in the exact same outline. So what is the reason for these melt holes? When I investigated this, I found out that in red outline on the right image is a volcanic platform. It's called the Maud Volcanic Platform. It's home to at least 4 very prominent cone-shaped features, and I believe that it's very actively emitting heat flow on a sporadic basis. A pulse of heat flow in 1976 and a pulse of heat flow in 2017. So it's a much better explanation of why this melt hole is here. We kind of talk about now some overall things of the Antarctic continent. We start by talking about the Pacific Ring of Fire. The Pacific Ring of Fire is actually not a ring. It's actually a horseshoe-shaped. It's the most active geological feature on Earth, and it extends down towards Antarctica, where scientists up to now have said the Pacific Ring of Fire ends. What we've just reviewed is a lot of volcanic activity along the Pacific Ring of Fire. So I did some more research, and what I found out was that the Western Arctic Rift, which on this image is listed as shown as red hatched area, contains an impressive number of volcanoes. On a per square mile basis, the same distribution of volcanoes as the Pacific Ring of Fire areas. Summary of Antarctica: it's geologically active. It's definitely not a static bedrock platform that just holds ice. We've shown that heat flow and chemically charged fluid from its geological features actively alter animal migration patterns, plankton blooms, the chemistry and temperature of adjacent oceans, and most notably melting of glacial ice in Antarctica. Now we're going to talk about the Arctic Ocean region. Imaged on the left is the most intense phase of Iceland's E volcano eruption. I can't really pronounce Icelandic. I tried, so I'm just going to call it the E volcano. This eruption occurred on April 14th of 2010. You can see it on that left image. It was a very intense eruption. It lasted 37 days, emitted 330 million cubic yards of sulfuric dust into the atmosphere. To let you know, that's a lot of volcanic dust. It resulted in changes in air traffic, cancellations across Europe, caused a lot of human health problems, animal health problems, and acted to significantly alter weather conditions in and around Europe. However, the most important aspect of this eruption was that it was a dramatic visual confirmation that the Arctic region is significantly more geologically active than previously realized. So the public really took note. On the right slide is just one of my favorite slides. It shows the initial eruption of the volcano and how it's spreading volcanic ash across the glacier. It also shows how it fractures the glacier and connects down to the bedrock. Next, let's take a look at the regional aspects of the Arctic region. The large-scale features of the Arctic region include the 3,800-mile-long mid-Arctic rift and its associated active volcanoes. This rift is shown on the right side of the slide as kind of a long, sinuous, red-hatched area. The triangular red areas are the known active volcanoes along the rift. Also shown on this slide is the Greenland-Iceland mantle plume. You'll see on Greenland the words are relic heat flow. That's the former position of the Iceland mantle plume underneath Greenland. And then if you follow that to the right, you can see a circular area. That's Iceland, which is the large mantle plume area. Also shown on this map, kind of in the center on the bottom, is the Baffin Bay Labrador Rift System. It's a red-hatched kind of thumb that comes up there. Lastly, on the far left of the slide, in red-hatched with red volcanoes, is the Aleutian Island Convergent Plate Boundary. For those of those who don't know what it means, it's where two giant plates collide. One dives under it, and it creates a tremendous amount of volcanism. As you've noticed in Alaska, there's a lot of volcanism going on. This system also goes to the north and just off the slide and connects to Russia, where there is a large volcanic platform there called the Kamchatka Platform. So we're going to talk about some of the features in this region on the east side, specifically the Antarctic Rift System. This image kicks off that discussion about activity on the eastern side of the Arctic Ocean region. What you can see here is extent of Arctic sea ice in October 2017. And this is representative of most of the last 10 years of Octobers, the sea ice extent. You can see the gray areas of Greenland, Canada, and Russia up there. What you'll notice is that those red hashed areas are actually the average extent of where the sea ice should be across about the last 50 years. So the current sea ice extent, October of 2017, is shrunk. There's less ice. It's melted. And it's melted in two specific areas. On the left hatched area, adjacent to the sea ice, there's distinct melting. And on kind of the upper right, extending down through Greenland, and there's a little red hatched area next to Greenland right beneath it, is the eastern edge melting of the sea ice. This melting of these two specific areas has been going on for a long time. It kind of begs the question, why aren't other areas of the sea ice melting? You can notice that the sea ice extends up close to Russia. Why isn't that area melting? Why isn't there melting along portions of Canada to the south? Or why isn't the center portion of the sea ice melting? Well, there's a geological reason for this. This is the first geological reason of that. The map shows the sea ice extent, and it shows some red-hatched areas. These red-hatched areas represent a strong concentration of methane in the atmosphere that occurred very suddenly on April of 2014. This methane concentration was captured by NASA satellites. Also shown on here is the black lines. These represent the center of the mid-Arctic and Baffin Bay Rift and kind of some of the cross faults. These center lines are where lavas come up and spread out. So how did this high concentration of methane get there? It began in April of 2014 when a moderate earthquake located along the mid-Arctic Rift resulted in the shifting of deep magma chambers, the spreading chambers. The shifted magma chambers released heat and hydrothermal methane into deep portions of certain segments of the rifts. This heat and methane moved upward along the deep fault plane, now opened from the seismic activity, and in the process the heat encountered horizontal layers of what are called methane clathrates. Now, for those who don't understand, these are kind of sediment beds that have ice in them, and frozen in the ice is massive amounts of methane. So when the heat encountered these horizontal layers of clathrates, they melted the methane. The methane, in addition to the hydrothermal methane, migrated up through the faults into the overlying ocean. The heat warmed the ocean. The methane, which is a light gas, rose upward through the ocean column and into the atmosphere where the NASA satellites recorded. So this is a reflection of a very geographically extensive heat flow event, and it gives you an idea of the power of the rift segments. Next, we talk about another example of Arctic sea ice melting on the eastern edge. Specifically on the left image, you can see marked there the Mayen trend. This Mayen trend is a 932-mile portion of the mid-Arctic rift that's volcanically active. On the right, you can see its position on the mid-Arctic rift. It's from just north of Iceland up to the Svalbard Islands. This particular section was the focus of research by the University of Bergen, headed by Dr. Pedersen. What they found really makes a strong point. I'm going to quote from the research summary that Dr. Pedersen put together. It is as the following: 2,200 degree Fahrenheit magma pouring into the seas from hundreds of submarine volcanoes. And we wonder why the seas are warming? Dr. Pedersen also went on to say, we have found volcanoes at such a shallow level they could break through to the surface at any time and form new island groups. Just for the record, I've been talking about underwater volcanoes for years, he said. In fact, there's an entire chapter in my new book, Not by Fire but by Ice, that discusses the importance of underwater volcanoes and how they're heating the seas. Well, this is a pretty dramatic statement by Dr. Pedersen from his research. I would also note that the end of the Jan Mayen trend is the Svalbard Islands. You can see it on that right slide. Research in this area has shown that there's an extreme amount of heat flow and methane being emitted in and around the islands, and that some of the glaciers on that island, a few selected ones, are melting while others are growing. So these facts indicate that the Svalbard Islands are also active. Next, we're going to shift south to Greenland and talk about bedrock heat flow across all of Greenland in one example, and then another example we'll discuss heat flow specifically in the northern part of Greenland. The left map is taken from an August 1st, 2018 research study by NASA. It documents the geological timeframe movement of Greenland across the so-called Greenland-Iceland mantle plume. The heavy black dashed line and talk about bedrock heat flow across the stable mantle plume beneath it in one example. Black dots and then another example will discuss and geological date specifically in the northern as it moved northwest across the stable and underlying mantle plume. Also on this map are color shading. This represents NASA's interpretation of the present-day heat flow of the rocks in Greenland. You can see that that heat flow map closely matches, especially in the central and southeastern portion, the course of the mantle plume. So this heat here, according to NASA, is relic heat flow that's captured, that occasionally pulses out of the bedrocks beneath the glaciers in Greenland. On the right image is a specific example of how this relic heat flow has affected the bedrocks and associated overlying individual glaciers. This is one of just several studies I could choose. It's in a location of Young Sound. The research was conducted by Aarhus University from Denmark. What they found was the Young Sound Glacier, imaged on the right as it's pouring into the Greenland Sea, its upward catchment basin lied on bedrock that was extremely hot. They decided that this was the reason this glacier was moving so quickly and receding so quickly, not atmospheric warming. So that wraps up our discussion about the eastern melting of the ice sheet and associated geological activity. Now we're going to take a look at the western side melting of the sea ice in the Arctic region. And this centers around what's going on in the Bering Sea. The left side shows the Bering Sea in relationship to the Arctic Ocean. The Bering Sea is basically a closed basin. The right side shows what we previously talked about in a little bit different orientation, the Aleutian Islands and their associated 90 or so active volcanoes. Off to the upper left portion of the slide, you can see the Kamchatka Peninsula and its 70 or so very active volcanoes. What's also important on this right image are the ocean currents. The Bering Sea is more or less closed, so the ocean currents move, for instance, from the Kamchatka Peninsula south, break through an opening, and move north through the center portion of the Bering Sea and eventually empty into the western portion of the Arctic Ocean. Additionally, you can see the major current on the outside or south side of the Aleutian Islands takes a turn, goes through a gap, and follows the eastern side of the Bering Sea, and this warm water empties into the western side of the Arctic Ocean. I here contend that this Bering Sea warming, which by the way is confirmed by numerous shallow sea surface temperature maps of the Bering Sea, is the Bering Sea is very warm and it empties into the Arctic Ocean and melts sea ice on the western side. Now we take a look at a major event that occurred in 2010 in the Arctic region. The left map shows the ocean current flow of the mighty Gulf Stream current in May of 26 of 2010. It illustrates that the mighty Gulf Stream current, shown in red, that's ocean water velocity, moves along the eastern side of the United States. It was suddenly blocked in 2010 by a large blob of warm ocean water. Now, I want to make sure you understand that that blob of ocean water occurred rapidly and extended from the surface of the sea all the way down to the ocean floor. So this was a very large and powerful warm blob. The lower right image shows the lateral extent of the blob in a little bit different version. This is early on in the development of the warm blob. Of note, you can see that the blob is kind of associated with heat flow. So the red is the warm blob. You can see kind of in the center part of the lower right slide, Iceland, and that there's heat flow coming off it. You can also see, very telling-wise, that the spreading center lines of the rifts that we've talked about, the Mid-Arctic Rift and the Labrador Rift, bound this warm blob area. To me, all this is really good confirmation that this warm blob was generated by a pulse of heat flow from the rifts. On the upper right portion of this slide, you can see an image of the 2010 eruption of the volcano that we talked about at the beginning of this. It's kind of interesting to note that the Gulf Stream shutdown occurred in 2010, and the immense eruption of this volcano in Iceland occurred in 2010. Now, I want to make sure you understand what I'm not telling you is that this single volcanic eruption created this entire warm blob. Rather, what I'm trying to indicate to you is that the eruption signaled probably the end of a lot of heat flow that was active along the rifts in this southern area. And this was just kind of the climactic end of that pulse of heat flow, a heat flow pulse that created the blocking warm blob of the Gulf Stream current. In summary, the Arctic Ocean, similar to Antarctica, the seafloor of the Arctic Ocean is not this static bedrock platform. I'll leave you with this 3D bathymetric image. Shows the elevation on the floor of a portion of one of the rifts. You can clearly see there are some circular features in here that are cone-shaped. Those are deep ocean volcanoes called seamounts. You can see some long linear valleys in here and uplifted mountains. These are very active faults. Antarctica clearly affects the bottom melting of the sea, the heat flow on these faults clearly affects the bottom melting of the sea ice, the temperature and chemical changes of seawater in and around Antarctica. It also changes the migration patterns of land and animal pattern of animals in this area. Other evidence supporting the broad regional activity of the Arctic Ocean area are that recent research shows that instead of having large earthquakes along these faults are what are called ultra-slow moving rifts or faults, and they have thousands of microquakes on a regular basis. So they've kind of gone unnoticed to the scientific community. So these other evidence supporting the activity in this area is from research that showed that some segments of the rifts actually capture seawater, push them down 15 kilometers where they get warmed and pushed back up. They've been termed kind of heat flow engines. So again, these have kind of gone under the radar because these are areas where there's microquakes and they didn't realize that seawater was being pushed actively down deep into the inner Earth regions. Now we move on to the Western Pacific Ocean El Niño-La Niña event. This is one of the most influential events, El Niño, on Earth. It's a climate phenomenon that originates at the same exact point. It has tremendous effects on ocean currents, animal migration patterns in oceans and on land. It's also been considered to be the active reason that several civilizations in South America shut down and moved. I contend that El Niño is created by a geological force. Evidence for that is as follows. All El Niños, as per the left slide, have originated at the exact same deep fixed ocean point located in the offshore region near Papua New Guinea and the Solomon Islands. This area is one of the most volcanically active regions on Earth. El Nino sea surface temperature maps, which is kind of this bright map on the left, show that this is a very intense event. The boundaries between the red warmed areas and the cooler yellow areas is very definite, inferring that the energy source is very powerful. The shape of El Niños is not like any other shape in the Pacific Ocean or the other oceans. There, the ocean currents kind of swirl things. I mean, you are used to seeing swirling hurricanes in the Atlantic Ocean powered by ocean warming. You're used to seeing swirling cyclones in the Pacific Ocean fueled by ocean warming. That's not the case with El Nino. These are long linear events. And El Niños don't occur anywhere else on Earth, just this one spot. So the analogy to that is in the upper right-hand image. This is an image of a terrestrial land volcano erupting and sending ash with air currents from the left side to the right side. That's kind of what El Niños do. Ocean currents carry the warming from the west or left side to the right side to South America. Another interesting aspect is on the lower right line. This is a snapshot of a time video of the warming of an El Nino. The warming does not occur in uniform fashion. Rather, it occurs, according to these time-lapse videos, in distinct pulses. So there'll be a pulse of very high heat flow, a circular contained one, originate from the source point and move and stay in together all the way to the west over to South America. Eventually, the cumulative effect of these pulses makes the image you see on the left with this definite kind of cone-shaped feature. Also of note is that climate models attempting to simulate when El Niños happen consistently fail. I think the reason there is that they're using atmospheric forces and side effects to model the occurrence of it. And secondly, volcanic eruptions just don't happen on a regular basis. They're much more erratic. Also, it's of note that El Niños are not really increasing in intensity through time. Spanish explorers observed, and people in South America observed, very strong El Niños. Like I said, moved entire civilizations back to 1525. This is just a broad look on the left of the point source of El Niños relative to the expanse of the Pacific Ocean. You can see that the point source is definitely a small area. It represents about 1% of the Pacific Ocean. On the right is kind of a close-up look of the position of this point source along the Pacific Ring of Fire. And you can see the black lines, the main fault of the Pacific Ring of Fire, and the 5 or so other very active plate boundaries associated with, or faults associated with, this point source area and the numerous volcanic areas that are actively erupting all the time in this portion of Papua New Guinea and the Solomon Islands. While we're on this slide, let's talk about why has this specific ocean area remained hidden from geological analysis. The answer is a combination of two things: insufficient data and atmospheric bias. Concerning insufficient data, Earth's oceans cover 140 square miles of our planet's surface. However, there are only 3,881 ocean buoys that record the temperature of the ocean. This equates to one buoy every 36,000 square miles. Furthermore, the main constraint on these buoys is that they only measure the surface, or when they dive down to about 6,000 feet, the 6,000 foot level. The area of this source point is at 12,000 feet, and in some portions down to as much as 20,000 feet. So the buoys never reach this deep ocean point source, so the heat is carried away laterally before the buoys can identify this point source. Concerning the atmospheric bias portion of this, like we spoke of before, scientists, well-intentioned, have looked for reasons that El Niños start in this area based on atmospheric and shallow ocean data. They gave up several years ago, stating that instead El Niños are developed by some unknown natural force. In February of 2005, there was a very large swarm of seismic activity. 4 months later, in a lagged fashion, El Nino developed off to the east in South America. This confirms what a lot of the researchers have contended, that seismicity is associated with all El Niños. So how do La Niñas form? we know that El Niños form from a pulse of heat. So this part of the presentation I want you to know is, I consider an idea, not even a hypothesis, but I think it's worth mentioning and getting out there in the public. The reason La Niñas form, in my opinion, is that as the magma chambers at the source point cool down and the fractures and faults above them still stay open, seawater is still circulated through this fractured system, but it's much cooler seawater. Also adding to that is the fact that methane clathrates, which we talked about before, icy formations that fill these faults and sediment layers associated with these faults, reestablish themselves, and they act to very rapidly cool the ocean water. On the right is kind of an example of this. This is an image, a graph I should say, from 1995 to 2010 that shows all El Niños in red, temperature-wise, and then all La Niñas in blue, and then the areas where it's kind of normal temperature, there's no color. I want you to take a look at the 1995 El Niño event. You can see that it went from a peak of very warm and almost instantaneously went to a peak of very cool blue. The energy required to do this is immense. It's actually more energy than is required to form an El Niño. So this transition event, which other scientists have noted, occurs on a regular basis for more strong El Niños. You can see in 1990 that happened, in 2000 that happened, in 2010 this happened. So I think this strengthens the notion, as per my idea, that the methane clathrates play a strong role in creating very rapid cooling. Now we shift gears from ice ages to El Niños and La Niñas to how plate movements control ice ages. This is a map of the Earth, kind of spread out flat. You can see in gray Africa, South America. On the lower part of the image, that's glacial ice sheets. Schematically represented, this is about the major extent of the last 4 ice sheets. In red, you see these very prominent long linear features with a black line in them. These are the ocean floor plate boundaries. The red indicates that these are very active sediments. The cooler colors are older sediments. You can see that right along the ridge centers, the spreading centers, the rock is very, very young and likely emits lots of heat flow. So now here's an interesting fact about ice ages. Just released research by MIT just in this last month has proven that so-called ice ages are caused by plate collisions, thereby confirming an old tenet of the plate climatology theory that geological forces have an immense influence on climate and climate-related events. A climate-related event like glacial periods. The research showed that every 100,000 years, Earth's orbit around the sun alters for a very short time period. So it acts to put stresses on the plate movements and, as I think, a resulting heat flow pulse every 100,000 years from these plate boundaries. Research by Lamont Doherty in 2005 confirms that every 100,000 years, deep ocean plate boundaries emit massive amounts of heat flow. So this research and the MIT research combined together, I believe it shows that for a long time, plate movements have dominated basically the climate status of Earth. This is a graph of Earth's atmospheric temperature over the last 400,000 years. So 400,000 is on the left, on the right is 1950, which is represented as present. You can see that the cool periods, which are the ice ages, represent the vast majority of time. You can see that the warm periods, the red, represent very, very short times. You can also see that, like El Niños, the transformation from a very, very cool event or an ice age happens almost instantaneously. I contend this is from this heat flow from these plate boundaries. You'll also notice that many of the warm periods actually are not warm periods. They actually start temperature cooling immediately. So look at the one at about 325,000 years, the one at about 30,000 years and the one at about 125,000 years, you can see ice age temperature in the atmosphere ends and warms very rapidly and then immediately starts to recover. That's also true, by the way, of our current warming trend. If we were to expand out to look at that, you can see that there's a peak of warming very early on, and then it slowly starts to warm. Now, not to say that these warming events don't stall a little bit. You can see that they're kind of jagged. They kind of go up and down. And that's kind of what's happening in our current warming event. You'll have periods where there's some cooling, and then periods where there are some warming. The current warming event has been going on for about 12,000 years. And as you can see, it's about time to end. Taking all this information together, I'm going to make a probably hotly debated hypothesis. My hypothesis is that there is no such thing as ice ages. Actually, there are warming events that happen every 100,000 years, and the Earth immediately starts to recover back to its normal climate state of cool atmosphere, kind of in an irregular pattern, but it tries to do it, and then every 100,000 years, another pulse of energy from the plates disrupts that active recovery. So I propose there are warming events and Earth's natural climate status and extent of ice ages, which is much greater than we think. Now we move on to a brief discussion of terrestrial volcanic emissions. There's no way to do this justice in a short time period. I'll hit a few highlights. Everyone is fully aware that major volcanic eruptions affect climate. On the left, in April 2015, is the Calbuco Chile eruption, which disrupted the temperature of the atmosphere for over a year. On the right is the 1816 Mount Tambora eruption. It's the caldera, which acted to create what was called the year without a summer. So it was a very, very cool summer there. So that volcanic eruption affected the climate of the Earth for a year. There's much more to say about continental volcanic eruptions. Research over the last 5 years has now shown that all the major extinction events of animals and plants on Earth and in the oceans was the result of volcanic activity. Let me repeat that. All the extinction events through many hundreds of millions of years are caused by volcanic heat flow. You may not understand exactly what these ages mean, but the Permian extinction age, the Triassic extinction age, the Jurassic extinction age, and one that you'll probably know, the Cretaceous extinction, the K-tree boundary, which has up till now been called the asteroid dinosaur ending extinction. Turns out that research over the last year shows that the asteroid did not cause the extinction. What caused the extinction was volcanic eruptions in an area in central India, a huge area. Land volcanic eruptions emitted massive amounts of dust into the atmosphere. This area is called the Deccan Traps area. So research has shown that this area was the cause. How did they prove that? They know the exact timing of the asteroid strike through dating of sediments, and they know the exact timing of extinction events in the Cretaceous age. These extinctions of various species started to happen and almost were finished way before the asteroid hit. So the asteroid is not the cause of the extinctions. It may have helped a little bit at the end of it, but there's even now research out which shows that that asteroid strike may in fact be a supervolcanic eruption. Thanks for hanging in there with me. Certainly a lot of information to take in. Hopefully we've accomplished the stated goal to present evidence supporting a plausible alternative explanation concerning what forces influence, alter, and in some cases control Earth's climate and climate-related events. I'll end with kind of discussing this image above. This is an image of the most powerful geological system on Earth. They're called upper mantle convection cells. And the scale is correct here. They dwarf the size of the thin veneer of outer crustal geological layers. They dwarf the size of thin ocean areas. These systems are so dynamic and powerful that they have the power to move entire continents 2 to 3 centimeters per year. As per the plate climatology theory, I would contend that this is the driving force behind many of our climate trends and anomalous climate events. Certainly the atmosphere has something to do with it. I understand that, But it's time to really open our eyes and change our course in science and start appreciating and researching the effect of geological forces on our Earth. Thank you.